Okay, we are on Chapter 3, Part B, Transform Methods. This chapter is dealing with Fourier transform, discrete time Fourier transform, and also fast Fourier transform and its applications. So it's mainly discrete time Fourier transform, basically discrete time signal, and you're taking Fourier transform of that. That's the basic idea. It's called discrete time Fourier transform. And first I'll go through discrete time Fourier transform and the properties of them, and then I look at discrete Fourier transform. There's a difference between these two. Remember, this is a discrete time Fourier transform, taking the discrete time signal and taking a Fourier transform of that using a formula. Then this is a different way of calculating the same thing but at discrete points. I'll come back to that in a minute. Then padding with zeros and frequency zero solutions, then inverse discrete Fourier transform, and then we look at computational complexity. It's a very small chapter, but you really need to understand this chapter. So what is the discrete time Fourier transform? I've taken this from your reference book number 1, reference 1. Fourier transform of an arbitrary discrete signal, which we sometimes call as Fourier transform or discrete signal. And they don't use this terminology anymore. It's all discrete time Fourier transform. It's called discrete time Fourier transform. What does that mean? The definition is like your Fourier transform pair for a continuous time signal that I have explained that in Chapter 2 and Part B. If you take a discrete time signal, the Fourier transform pair is now defined as this. What you are trying to calculate is x theta, that's your frequency response. You take your discrete signal, multiply by e to the minus j in theta, and sum them between minus infinity to plus infinity. That's the definition of discrete time Fourier transform. And then if you look at the inverse of that Fourier transform pair, as how to find x, then you go 1 over 2 pi, because we know x theta is fundamental period is between pi and minus pi. So we go for minus pi to plus pi, x theta, and this will become plus j in theta. And this is minus, remember, and that's plus, and 1 over 2 pi, which is a scaling factor. This is called the discrete Fourier transform pair, similar to the continuous Fourier transform. So the similarity is still there. Okay. So from now onwards, we say if you have a sequence, leave out the terminal FTD. You say if you take discrete time Fourier transform, you get x theta. And remember, x theta is continuous. So if you find x theta for a signal, we don't know the signal, it's plus the magnitude, they are continuous in the range of minus pi to plus pi. Whereas if you have got an analog signal xt, and if you take Fourier transform x omega, they are discrete in nature. But anyway, leave that for a moment. You've already done that without confusing anything. Let's go for this. So x theta is a continuous variable. So this is theta. Okay. So from now onwards, we will say that these are the two pair of discrete Fourier transform. We'll be using it. If you know the signal, discrete time signal, and you want to find out what sort of frequency content it has, then you evaluate this summation. If you've got already a frequency response of a signal, it is a phase as well as magnitude, and you want to get the original signal back, you evaluate this integral. And we will find later on there are quicker way of implementing. This is the most accurate way of implementing it. And theta is the digital frequency as we know, and theta is between minus pi to plus pi, and theta is defined by omega ct is the sampling frequency. X theta is periodic with a period 2 pi, we know this, and x theta plus 2 pi is x theta. So remember, if you've got a fundamental spectrum here, pi and minus pi, and that spectrum will repeat. You've learned that before. That's why it says x theta plus 2 pi is x theta. That means if this is x theta, this is pi, at 2 pi is just the repetition of that spectrum. Minus 2 pi is repetition of that spectrum, and so on, and it just keeps continuing. So this is just the summary when you are writing the discrete time Fourier transform. The discrete time Fourier transform equations you are given. You don't need to remember, and all you need to know is how to apply that to find frequency response. Let's take one simple example. Like, oh yeah, this is what I said. The Fourier transform of an analog signal is not periodic. It doesn't go periodically. Okay, you've seen that in chapter 2. Now we go into example. Here is a discrete sequence, which is a delta n sequence, and I want to get x theta. That's the frequency response. Summation minus infinity to plus infinity delta n e to the j minus n theta. If you evaluate this, all you will find is that n equal to 0, this become 1, that become 1, so totally 1 is the answer. In other value, n not equal to 0, delta n becomes 0, the summation only leads to one term. Therefore, we know that x theta, that should be capital X theta. And this is so to half the sampling period there is now continuous signal. That's wrong. That's continuous. It's not discrete, it's just continuous, x theta. Whereas x omega would be discrete. Just for the analog signal. Okay? So take another example. Let's take one more example. I have to find discrete time Fourier transform. Here's the signal given to you. If you plot that, that could be a signal like that or like this, depending if A is greater than 1, A is less than 1. Now if you take this signal and find x theta, use the formula. And you go from n equal to 0 because it's 0 when n is less than 0. So your summation starts from n equals 0 to infinity. And you evaluate this. When you evaluate this, this becomes a power series, which is 1 plus a e to the minus j theta plus a e to the a squared e to the minus j 2 theta plus and so on. And if you take the summation of that, you get it is 1 over 1 minus a e to the j theta. And if you want to expand this one, you expand in this form. And if you want to get the magnitude response, that's taking the real part and imaginary part of the complex number, and the magnitude response is that. And if you want to get the phase response, you need to take the complex conjugate, multiply by complex conjugate up and down, and then work it out. Your phase response will become as minus tan inverse of that. You can cross-check that. So to get phase response, basically what you do, you multiply by complex conjugate that, and a minus of that on the top, then on the bottom, and then after that, you just get the phase value. So that's how you calculate the x theta if you are given xn. So this is given xn, this is given to you, and you're calculating discrete time Fourier transform using the formula. And if you plot this, it tells you the next stage. I think it shows you, if you plot the graph, and the modulus value, the magnitude value, that's not right, that's x theta, modulus of volt. X theta is 1 over minus a, and at that point. So this looks like this is theta axis. This looks like a low pass filter. And if you plot the signal itself, that is a to the n, un, you plot the signal itself at t equals 0, it's 1, amplitude is 1, here's all zeros, and the signal behaves like that, and that's the signal, and that's your discrete time Fourier transform you do, and then you plot the magnitude of x theta. So if you are given a sequence, you should be able to apply this formula to get the Fourier transform. What's the Fourier transform tells you? What sort of frequency is available? Now, you can see that there are other ways of calculating theta as well, which you have already done before. What you do is the other way is, without using the formula, you start with xn, which is given, then you find the set transform. Once you know the set transform, then you substitute x theta equal to x hat and set equal to e to the j theta, and you get this. That's the second way of doing it. So if you've got a sequence, you find the set transform of it, and then substitute. That's one way. Second one, directly apply the formula. Sometimes you can't apply directly the formula because it's very hard to manipulate. So this becomes easy. Now remember that we always refer x theta mean, which is x e to the j theta, because we are substituting that equal to e to the j theta. Let's take another exercise. Here is a rectangular window you have. You can see that? A rectangular window. It's symmetrical. So xn is equal to 1 when n is less than or equal to n, modulus n. That means there n is 2 in this case, and 0 outside the range. Mod means you know this, yeah? When n is less than n, so n is greater than or minus n. So if n is 2, so you go minus 2 plus 2, within that those are the samples. And you've been asked to determine x theta. So you go back and apply the formulas as the way I did it, and you can show actually it is sine theta over sine n theta. So the answer comes as x theta in the form of sine n theta over sine theta form. That's the form you get. So you must try this example yourself and see whether you are able to get that answer. That's kind of a sort of sinc function form. We actually, this is another signal. This is a cosine waveform in MATLAB, and if you take the discrete time Fourier transform, whatever the frequency you work out, that's your center point. You get your signal there, that frequency, and also symmetrically you got there as well. You will have all these ripples because you're taking a rectangular window, because you're grouping a signal like from there to there. So as soon as you group a signal, you have this rectangular window effect comes in. That causes all these problems. If your window is very, very large, that means if you take this signal of infinite length, then you will end up with all these sharp peaks like this, with virtually these are zeros. This effect is windowing effect, that's making the window small, causing this problem of a ripple. You will probably come across this again later on in filter design. But for the moment, you need to know how to use that formula. So you go in, instead of xn, you put cos n theta, and once you're done cos n theta, evaluate the summation or use the transform to get your discrete time Fourier transform. Discrete time Fourier transform, discrete time is only the time signal. Fourier transform, which is continuous here, like you got values for every frequency point. In the same thing, I just implemented using MATLAB, and same signal how to generate and how to get discrete time Fourier transform. So many ways of doing discrete time Fourier transform, and you may have a look at this one and see how I have implemented it. But I won't go through it because you're doing it in the lab anyway, so you can understand the MATLAB code. Now, we just look at the properties of the Fourier transform, discrete time signal. Well, we don't use that, we use a discrete time Fourier transform. So we say xn is your signal. You take the Fourier transform or discrete time Fourier transform, which becomes x theta. x1n become x1 theta, x2n become x2 theta. So the linearity property says, again you don't need to prove the properties, a x1, x1n, b x2, and if you take the Fourier transform, discrete time Fourier transform, it will become a x1 theta and b x2 theta. That's one property. Time shift property says if you delay your signal in time domain, in the frequency domain, what will happen is it gives you an exponent e to the j theta k, like that's the phase, introducing a phase plus x theta. And if you want to prove it, you just say xn minus k, take the Z transform, you get Z to the minus k xz, substitute that equal to e to the jk, then you do that, you get that one automatically, what you want. Now, what about that time shift? This was time shift, shifting the signal in. What happens if you shift the signal in frequency? So this is your analog discrete signal. You multiply by exponential n theta naught. That means cos n theta naught plus j sine n theta naught. If you do that, we can actually show this one works out to be x theta minus t naught. That's exactly the same as this. This is just another symbol. What does this tell you? What does this tell you is that if I have x theta like that, that's my x theta minus theta node is, if theta node is there, this is shifted to the left somewhere here. So that's what it happened. So when you take your time signal, multiply by a cosine function or sine, well, a complex function, when you do that, you will get this frequency shift. When you multiply by cosine only, rather than this, which you should work it out, you will find you'll have got two shifts. One is theta minus theta naught, other one is x theta plus theta naught. And the amplitude would be half here and also half. That's only when this is replaced by only cosine value, nothing else. So if you have complex, then only you get one signal, one spectral shift. If you have got cosine, then it will shift both sides. So this means it's not only, where's the diagram, not only shifting here, it will shift here as well, minus theta naught. But the amplitude, if this was 1, this is all half. Important, you will learn that under your signal processing part A, with different sections on multi-rate systems. You'll do that. Okay, let's now come back to one or two examples. And these examples are very, very important, that you really need to understand these examples. You are given a frequency response of an ideal low-pass filter. Low-pass filter is ideal. So in this case, the low-pass filter, if you draw the diagram, it looks like that. It's pi over 4 is the cutoff frequency. Theta c is pi over 4. So that's pi over 4. That's pi over 4. That's minus this is h theta. And that's theta. And you've been asked to find the impulse response of this ideal low-pass filter, and then find the impulse response. First, find the impulse and sketch the impulse response, and you'll be given the frequency. So what do you do? Impulse response means if h theta is given, you have to find hn. So you use inverse discrete time Fourier transform formula. So if you are given h theta, you can find hn. So let's apply that. In the first slide, I showed you Fourier discrete time Fourier transform inverse as well. So you use the inverse to calculate this. So here is your equation. Here is the diagram. Given as half the amplitude given, this is theta c, theta c. So inverse discrete time Fourier transform tells you that hn is equal to 1 over 2 pi minus pi 2 plus pi h theta e to the j n theta d theta. Don't forget this is plus here. Plus j n theta. Now I substitute, what I do now is, I substitute, this doesn't go from minus pi to plus pi because this is all zeros. So I start from minus theta c to plus theta c. So integral goes from minus theta c to plus theta c. And the magnitude is half, this is half. So half is here, and e to the j in theta. If you integrate this, you will get 1, 2 comes out, that will be 4 pi, that gives you that one plus that one. And from here you can say this is like a sine formula. A sine is what? Sine theta is equal to e to the j n theta minus e to the minus j n theta over 2j from Euler's formula. We have done that before. We have done that before. So we can use that formula here. When you do that, what you will get then is this, you can take one of the 2 here and move one of the n out. So you'll get 1 over 2 pi left over, n is to the left, sine like that's what it was. If you plot the so cut off frequency. In theta over theta So the magnitude is going to be 1 over 8. So that is going to be 1 over 8. And then you substitute it over 1, you substitute 3, and plug them. They look like that. So that's the equation for the ideal low pass response. Sometimes in this case, the magnitude of response is given. Sometimes you're given with the phase. The phase as well. And in this particular example, basically, you go from minus pi to plus pi to inverse this this Fourier transform. The Fourier becomes from here to here, then 0, here to here, then 0, then here to here. You will have one term, two terms, three terms. And so you go down to one, three terms there or here. Which one goes to which you check it out. So you go and start doing this discrete you get the that. Now you say one more time, I learned by this. The mechanism is one. And then you go I over 6 amp. That should be minus pi over. And the other should be line selection should be with the second thing. So then when we get that, then pi over 3 combined with the so if you integrate this one, this is the first part of the reciprocal. And then you substitute, you can say now on the opposite. Now you can say you're going to combine this with that, so this, then this one, is that correct? Now we move on to discrete time Fourier. Discrete Fourier. So far we talked about discrete time Fourier which is continuous. So we say extent is available. Discrete time Fourier comes to extent. Then if you have got and then you go back to simulation. That's called discrete. Then you have got which first time you come to us, which is something here x theta minus x theta. Discrete time like that. I and now I can find the way of finding values the x theta. And if I can record those values the output is not continuous, but it's a discrete value. But if you join the envelope, it looks like x theta. So the question is, what does that mean? What does that mean is this: if you take x theta, theta is defined algorithm that you use for discrete Fourier transform is called fast Fourier transform. It's an algorithm to calculate these discrete frequencies very fast. When you calculate the discrete frequency, it gives you the magnitude and then the phase as well. So basically, what you do is this. Can I go back? What you do is you are given xn and you use discrete time Fourier transform technique, you get x theta, which is continuous. And if you then have to plot, you will see the waveform and you will see the waveform. But we don't need. If you take the same signal and if the signal only has certain frequencies, not every frequency, you use discrete Fourier transform, which will tell you, well, which frequencies will come in a minute. It will tell you, here is a DC available, that. It analyzes equal intervals. And if you use that, that's more than enough for any application. Not only that, you can implement them this month very fast on a computer using the FFT algorithm, fast Fourier transform algorithm. It's not FFT is not a transform. A lot of people think it's a transform. No, it's a fast algorithm. DFT is to transform, discrete Fourier transform, right? So DFT is mapping xn to another sequence. So when you finish DFT, what will happen is you get xk's. So from a time sequence, you are getting not a continuous, but a frequency positions, frequency values, discrete values. DFT denoted by xk allows to evaluate the Fourier transform x theta that you want to evaluate that. This complex value sequence xk, this is what is obtained by sampling the Fourier transform x theta. So if this is your x theta continuous one, you sample that. And it's called frequency sampling. So you've got a frequency continuous signal, you just look for, not like a time sampling, you've got an analog signal, you look for digital value. In the frequency, you've got a frequency spectrum, you look for discrete value. That's called frequency sampling. That is exactly what this does, DFT. This sampling is conventionally performed on equally spaced points on the unit circle between -5 to +5. So, you want a discrete Fourier transform of a signal, you take the signal, write an equation, and you evaluate that, you will get discrete Fourier transform that will be at different position k. K could be starting at 0, 10 Hertz, 20 Hertz, 30 Hertz, 40 Hertz, and so on. You could ask me a question, why it has to be 10? Can it be 12? Yes, it can be 12. If you start with 12, then it's 24 Hertz, 36 Hertz. Equally spaced. You can't have 12 and 25, okay? They have to be equally spaced. DFT allows us to determine the frequency content of a signal that perform spectral analysis. DFT plays a central role in the implementation of a variety of digital signal processing algorithms. And the efficient algorithm of DFT is FFT. So, summary. Okay, you've got a discrete sequence. You want to find out what frequency content it has. You've got two options. One is to write a big equation and solve it, you get x theta, which is continuous value. Or you say, no, I'm not interested. I'm only interested in the frequencies available in it. So you use discrete Fourier transform, which will only test certain frequencies only, whether they are available, and then tells you the amplitude and the phase. And the way of implementing is fast Fourier transform technique. So, Fourier transform of a discrete time signal, which is discrete time Fourier transform. X theta is that. That's the way you evaluate. The second method is you find x theta, you find x hat, and then substitute. And the third method is this is too tedious for complex signals. When I say it's not complex value signal, just a complex sequence, like, So the next method is discrete Fourier transform, which you go back to your x theta, this is your x theta, which is equal to what? Sigma n equal to 0, n minus 1, that's the sequence, xn, then you normally say e to the power minus j in theta. Now, how am I going to get x theta from here? You're saying x theta now becomes xk. K means I take the unit circle and find out the first frequency theta equals 0, then next frequency, they are equally spaced. So I could say 2 pi is divided by n points. You want 256 points, frequency positions. So you can now say theta can be replaced by 2 pi over n k. So k is the frequency position. 2 pi n over k. That's your equation now as a discrete Fourier transform. So the sampling x theta at n equally spaced interval gives you this new equation, which is discrete Fourier transform. Again, we will give you either this equation or the other equation in an exam. You should be able to write one or the other. Once you are given one, you can write the other one easily. So from now onwards, this is what we will use to extract discrete Fourier transform to look at a spectral content of a signal. So what does that mean? Here, look, you can see DFT corresponds to sampling the set transform and n equal points. So what I do, I go and say first frequency point is that, second one is this, third is this. So 2 pi is divided by n is the number of points you want. So if your h theta is like this is your x theta, You say, I want to look at frequency there. So 128 points here and 128 points here. So I say 2 pi over 256 is my frequency division between those. That's called my resolution, delta F. So you decide. So if you want very close frequencies to be determined, then what you do, you increase the frequency number of points. You will come later on in signal processing 2, you will find you can't have very close frequency precision because your discrete Fourier transform cannot evaluate. There is a minimum distance that you have to maintain, and that's, I won't touch on this later on, you will learn that. So this is a typical example of a fast Fourier transform implementation of a signal, and here's your signal. You use fast Fourier transform explained there, and this is your two frequencies you have got and occurring here. This is now become as K. K is your frequency positions, and now you can translate K into how many. So if I have K is 5, then I will say 5 times of delta F is my frequency. Delta F is my frequency resolution. So to summarize, what do we do? Here is my signal. Then you want x theta, modulus x theta. You do discrete Fourier transform. Come from here, you get that. But sometimes it's very difficult to evaluate. So the preferred way is from there, you go fast Fourier transform, and you get, instead of getting this continuous frequency, you get at different sample positions. And if you join them, you should really get this one back. So it's called n frequency sample points. When you do discrete Fourier transform, we will always assume, and also we can prove, the number of time samples you take to get the FFT of a discrete Fourier transform, you get number of frequency points. For example, if you say, I'm taking n time samples, you will find you end up with n frequency samples when you come through this technique. So you say 100 time samples I took, you then looking at 100 frequency points. I took 1,000 samples, that means I'm looking at 1,000 frequency points. That means the unit circle 2 pi is divided by 1,000. So you can see the resolution delta is equal to, you could say I have got 2 pi over n, and n is your number of samples. When the DFT of a block of n samples is calculated, the assumption is that the original signal actually repeats itself periodically. So if you put a signal like that, and you take a block of 100 samples, and so you're trying to get DFT, DFT assumes that block is now repeating. That's what DFT assumes. So you can see naturally original signal was continuous, like, nicely continuous. At that point, this has to start again. So there's a discontinuity you are introducing. So that is a problem in DFT. When you take 100 samples or 1,000 samples, you're truncating the waveform, and the DFT assumes that waveform is repeating. That's the assumption of the DFT. I won't go into detail of the assumption. And you can read on the book. And that assumption causes a problem. You can see here naturally, this is my next part. But DFT assumes that part is repeating. You see? That part is repeating again. That means instead of going smoothly like that, I'm going like that. That means I've caused distortion. So in a DFT, when you do analysis, there will be high frequencies will be introduced unnecessarily with this windowing technique, because we're taking group of samples, means there's a nice window. Like if I want to select, if 10,000 people are going, I only want to look at 100 people, what you do? You look through a window, to a 100 people window. If I want to see 1,000 people, you use a window of 1,000. That grouping causes a problem because of this thing. So therefore, there is all sort of this windowing process introduces a kind of a distortion, but there are ways of reducing the distortion or minimizing the distortion when you are doing DFT. Very simple in DFT, like when you should try, take a signal, 2 sine waveform, and you should try DFT using MATLAB command. For example, you say, if your signal is just your MATLAB, which is like create a signal, some value of something, and you say then is, you say H is equal to fast Fourier transform of X, and you can say 1024 points you want, and you can say magnitude is then is equal to absolute value of H. That gives you the magnitude, and then say phase is equal to angle ANGLE, angle of H, and that gives you the phase. Very simple in FFT. So this is your signal. It will be a 5 of 1024 samples. This is 1024 samples, and you took an FFT of that, and then you look at the magnitude, you look at the phase. So very, very simple. And then you plot the magnitude, plot mag and plot phase. Very simply, you can have a look at various things. Okay? So here is another example where when a 256-point DFT is taken using a rectangular window, that means here's a signal going like this, and what you decided is you only want to group that signal. I want to look at the frequency content there, because naturally the frequency content is varying. You can see it, like, So you just take the 256 sample and take the FFT of that, or EFT of it, and it tells you 256 frequency points, not more than that. And then you find out what is the F0 DC component, what's F1, F2, F3, F4, up to F128. Those frequency will be repeating this side because magnitude spectrum is symmetrical. Pi minus pi. They are the frequency points you are getting, and they will repeat here. So that's how the windowing technique works. And if you decide you want to use another window, you can start from here and go up to that. You can start from here, go up to that, and you can look at different frequency content of it. Let's look at one example of how to calculate the frequency, the solution and other things. Let Fs be the sampling frequency. Let number of time samples is 1000. That's time samples. 1000. So the frequency resolution will become F as sampling frequency divided by N. So 8 Hertz is our frequency resolution. So we could say the first is F0 is 0, F1 is 8 Hertz, F2 is 16 Hertz, F9900 is 8000 Hertz. So we will have 1000 frequency points. So naturally 500 frequency points on 0 to pi side, and the remaining 500 points in 0 to minus pi. So magnitude response, if you only look at the one part, it will be sufficient. So if I write the equation, this is what it is. That's how you evaluate. You first set k equal to 0 and find out x0, then set k equal to 1, evaluate this equation, and then k equal to 2, you evaluate this equation. So if you continue, that's basically how you evaluate. Take another example. A peak signal is sampled at 2,000 or 20,000 samples per second. So sampling frequency Fs is 20 kilohertz. That's basically it. And the sequence length is 1024 samples. It is selected, so we've taken 1024 samples like that, a window like that, and we do a 1024 point DFT. That's the terminology used. 100 point DFT, 256 point DFT. That means the time samples are 1024. If you do the DFT, first question is, what is the time duration of the segment of the speech? So the speech is like this, it's going like that. You go and put a window. When you put a window of 1000, anywhere you can start. If you start from here, say that's the window, that is 1000 samples. So you're starting at that time instant, finishing at time instant. The question is, what's the duration of the signal? So basically we know 1000 samples multiplied by the period, sampling period, which is 1 over 2 to 20,000, is 51.2 milliseconds. What's the frequency resolution? When you do this analysis, at what frequencies are you looking at it? The frequency resolution becomes sampling frequency divided by n, which is 19.531 hertz. So first frequency is 0, second is 19 point. If you have got a frequency at 5 hertz, you can't detect easily, but there will be an influence of that on both sides. And then twice of that frequency, 3 times, 4 times, 5 times of that frequency at the next position. So let's look at DFT calculation. How do you do DFT calculations? Let's look at the one. Okay. How do you do DFT calculation? That's our formula, defined formula, DFT, and we set k equals 0. So you expand this as cosine term, that's this cos plus j sine, right? So you have a cosine term and a sine term. You call this summation as AK, and this summation, this part is BK. So what you would have is xk is equal to, it's a complex, AK minus jbk. That's what it is. So if you want to get the magnitude of it, you take magnitude of xk square root of that square plus that square. And if you want to find out your frequency position, if you know what frequency, what position you're looking for, k equal to 0, then frequency is 0. K equal to 1 is the resolution, first resolution, second resolution, third resolution. If you want to find out delta f, your frequency resolution, take the sampling frequency, divide by n, will tell you the resolution. This is the lengthy procedure if example n is 1024 samples. Imagine if you have 1024 samples, you have to, for every value, you have to evaluate this first, and then evaluate this second, and then you square root and square. It's not easy. It takes a lot of time. So DFT computation is very complex. That's why you have got FFT algorithm. So when you do the magnitude response, this is how you see. You see your DC value here, then the first frequency, which is that's S0, that's your second frequency, third frequency, and then you got a pi, you get this, and then these all will repeat, all symmetrical, because this belongs to this side. So normally you plot only 0 to pi. The frequency resolution delta f can be made as small as desired by increasing the value of n. That's window size being analyzed. So if you increase n, if you want a very fine, small resolution, then you need to have a large window. A large window is not possible for non-stationary signal. For stationary signal like sine waveforms, so right. But non-stationary signal like speech, every 20 milliseconds changes. So you can't have a large window. You have to analyze every 20 milliseconds. Otherwise, the speech, the frequency spectrum that you get is completely average spectrum, which is not correct. Because the spectrum of the vocal tract, the whole thing changes, resonance changes every 20 milliseconds. So the window size cannot be made very big in a real signals, right? Here's another example that you've been given a sequence. Xn can be formed using this formula. That's an arbitrary sequence. You've been asked to find n point DFT. N is 50. Yes. So you can do this one using xstat, because you can take the transform of that, then substitute x theta. Now we know theta has to be divided. Theta is unit 30 here, and they have to be divided into. So you decide how many points, 50 points. So you can now say your DFT equation is that 1 plus 0.2, that theta, this will become this theta, is now divided by 2 pi over 50. So 50k, it will be 2 pi over 50k. K is the frequency point. So 2 pi over 50k and that. So that's your discrete Fourier transform equation. So if you are given a sequence that you know, you can formulate it using the transform and x theta. So here are the examples. You have to compute an endpoint DFT for this particular sequence. You have to then and show that when n equal to 8, the value H2 is 1. So let's go and try this one. Find Fourier transform of discrete signal, which is the discrete time Fourier transform, and the DFT of the 3 sample average. There's only 3 samples here, so we look at that. So if you write the equation, this will be minus 3 to plus 3. So it is from 0 to 2, otherwise 0, so I can switch them around. So then draw it. This is what I have. 1, 2, 3 value. Go back again, first again. This is the example that you have to try out and show this. Okay, so you should try this out. Here's another example that I'm going to go. This is an exercise, this is an example, where you've been told that discrete time Fourier transform have been asked to find for a 3 sample average here. So only 3 samples available. Each sample value is 1/3. So if you plot that, you get 1, 2, 3, and this is 1/3 actually. This is 1/3. And let's find out the discrete Fourier transform, which is equal to, right, this is the equation, Hn, that's that. N is, we know, N we can find N in a minute. And you expand this, that's what you get, because N is 3, 3 minus 1 is 2. So if you further continue this and expand this, just expand this one, you can show it is 1 plus cos that, 3 times that. That's your base value, that's your magnitude. So if you get the magnitude, that will become 1/3 of that bunch. And if you then change k equal to 0, 1, 2, 3 and substitute here, you will plot, you can have a graph which will give you, there should be a graph. We don't seem to have the graph, so it's okay. So this you can plot for different value of k. K is the frequency. So if you want to know frequency, k is equal to k times delta f will tell you where the frequency positions are. Okay, the next part is padding with zeros and frequency solution. What is padding with zeros? As I said to you before, that if you have a DFT could be any sequence. So like you could have 100 samples and take DFT, you get 100 frequency points. But I showed you earlier how to calculate DFT. You have to evaluate the summation, real part and imaginary part. It takes a long process. So people worked on various algorithms, came up, if this sample is made as power of 2, like 128 or 256 or 512 or 1024, they are power of 2. If you do that, you can devise an algorithm, new algorithm called SFT, which will be able to work very fast. So if you want to apply SFT, you must have power of 2 number of samples. But what happened in real time, in real signals, what happened? Say you sample the signal, real signal coming out, and you sample them. And you found you got 1,000 samples, but you're short of 24 because the signal only comes short time. You sample them fast, and that's it. You got 1,000 samples. You don't have another 24. So if you go for DFT, it takes a long time to process. So people said, if you have a shorter sample, what you do is to make up at 1024, you only have 1000 samples. To make 1024, so you go from 1000 to make 1024, these are your 1000 values, the sample. You put 24 zeros at the end. By adding zeros, you are not changing the amplitude of the waveform. If you think it carefully, no, you're not. What happens is, that's called padding with zeros. By adding zeros, you are making your number of samples 1024. That allows you to apply fast Fourier transform. And not only that, look at here. These samples are that, and by adding extra zeros, you are not going to change the summation. So you're not affecting the summation. But what you are doing is, your frequency resolution is sampling frequency over number of samples. So by adding a lot of zeros, you are kind of reducing the increasing the frequency resolution. But you know, you can increase the frequency resolution, but you're not going to get any extra information because your time samples are only the ones that you have. So the trick is, add extra samples, it does not affect your evaluation, but it aids you to apply fast Fourier transform. That's what it is all about, padding with zeros. So all it says, we want to find DFT xk, and that's your equation, k0 to 1 to n. To obtain more points in the DFT sequence, we can always increase the duration of xn by adding additional zero valued elements. This procedure is called padding with zeros. Only you have to add the zeros at the end or before, not in between samples. That's wrong. If you add in between samples, then you are changing the sampling frequency. That's not correct. You must add at the end or at the front. These zero valued elements contribute nothing to the summation. That summation does not contribute anything, and acts to decrease the frequency spacing. That means increasing the resolution, because n increases now, because you're adding extra zeros mean extra samples. So zero padding gives us a high density spectrum and provides a better displayed version of the plotting. So it just gives you a good display, but no extra frequency content now. It just does an interpolation actually. But it does not have a high resolution spectrum because no new information is added to the signal. It's just a display, but not spectrum. Only additional zeros are added in the data, but at the end of the data, or at the start of the data, it's okay. So let's take an example. Here is my 3 sample average. Here is my samples are 1, 2, 3. And I did Fourier DFT on it. I get 3 frequency point, 1, 2, 3, and this is a repetition of that. So how can you get the frequency response like that? You can't do that. It's just only this is only imitative. This one is like, I just knew it. I knew that's what it's going to be. So what I did is then, I introduced 2 more zeros to it, 3 more zeros to it. I made the number sample 6 there. And suddenly you see a value has been interpolated between those two by the discrete Fourier transform. You get another sample here, another one, another one. Now you can roughly join. You add further padding with zeros. The display gets better. So it's basically doing just added on extra zeros to make your graph nicer. So this is the effect of your earlier your distance between your frequency resolution was that. By adding 3 extra zeros, that means this is fs over 3 is your delta f here. Now delta f equals to fs over 6. Now delta f will become fs over 8. So you can see this is the delta f now. That's delta f earlier. Now this becomes delta f. So this graph is shown on the next page, and MATLAB program is written as well. And you can find this out in MATLAB that this is the original signal. That's my spectrum. It's in MATLAB. It looks like that. And then now added on lots of zeros at the end. And then got the Fourier transform. It did a lot of interpolation, and the waveform looks nicer. It's the same signal, same information at the peak end of it. Should be same value, the value should be same. So, summary, FFT is the way to go for it, and make sure your samples are power of 2, then fast Fourier transform can be added. And if you don't have power of 2, in MATLAB it will add on extra zeros to make it power of 2 so that it can run faster. So, discrete Fourier transform basically give you frequencies at discrete frequency positions, which is called K, which is multiple of the resolution. Inverse discrete Fourier transform. How do you do that? Basically, you go back to the inverse equation which we defined earlier, xn equal to 1 over n, that. However, the signal which it produces will be periodic signal repeating every n sample, because we assumed it was going to be periodic. So if it produces 100 samples, it assumes that 100 samples are repeating, right? Because you started with 100 time samples, you got 100 frequency points, and then if you take inverse, you get 100 time samples, and that's repeated. Clearly, DFT is useful and allows the spectral content of the signal to be determined. Additionally, once the frequency domain, the DFT signal can be processed in order to alter the signal in desired fashion. So if I have a signal here and take an FFT or DFT, I get just your magnitude spectrum. There, these are the values I got. I can actually modify, that's frequency 1, that's frequency 2. I can now go and modify this value there. I can increase this value out. I can, using a particular formula, and then I can reconstruct. Oh, I can make these all zeros. So I could have a nice low-pass filter in the frequency domain. So in the frequency domain, if you want to filter it, you just suppress the values, set the values to zeros, and then reconstruct the signal. You get signal without those frequencies. So there's lots of things you can do with the DFT. It really belongs to your next course where you really understand DFT very well. The circular DFT, circular convolutions all have to be done. But for the moment, the principle, why I'm introducing is just basic principle. The last part of the DFT is computations for evaluating DFT. Remember, we talked about it. DFT is the normal technique, inverse DFT is the normal technique. And it assumes that the sequence may be real. Your xn could be real. In a real signal, it will be real value. Or it could be complex, it doesn't matter. Mathematically, it could be both possible. So we could assume our signal Hn is real as well as complex. And when we do the Fourier transform, you get complex real part and a complex part. That's how you get the magnitude response from that. So if you start with DFT, that's DFT. Hk is what we are trying to find. Hn is your signal, and you write the equation. You now expand it. Hn is real and complex. So I make it just complicated for you for a moment. Normally, this part is not there. In a speech signal, it's only real. Anyway, having that, you expand that, you can see that to calculate that, you must do this first, and then you must do that, and then do all the summation, and add them all, you get k equal to 1 for one value. K equals 2 again, you have to redo them, k equal to 3. If you continue this, that's the DFT, and if you look at inverse DFT, the formula, same thing, you go for inverse, try them again, write them, and what you find is, what you have here and what you have here is almost same. Am I right to say that? Yeah, almost same as that and that, except the sign change. So FFT, DFT and inverse DFT can be implemented with the same formula, except in this is for DFT, and for inverse DFT, this will be frequency response. That's the change. Sign is changed. So really, if you devise an algorithm for DFT, you can implement inverse DFT using that algorithm. So people have gone through them and summarized them and worked out. You will find expect the scaling factor you always have in DFT 1 over n. If you work out DFT and inverse DFT, computations take 4n real value multiplication per point to calculate one frequency, and then 4n squared operations are necessary to compute n point transform. If you want to do n point DFT, you need to have 4n squared operation. It's a lot of, and in a computer it's not easy. If you do that using fast Fourier transform, which I haven't explained how to implement now, just only the principle behind it, which only need power of 2, n to be a power of 2. So if you just continue this process and analyze for various values, which I have got a table which you just get an idea behind it. I just quickly go to the table and I just move again just for one, quickly come back. Here's the table. I got 16 point DFT. I need 256 multiplication, and FFT only needs 32 multiplication. It's 8 times faster if you use FFT. It's an implementation. If you've got 2056 points, it needs 65,000 multiplication, and FFT needs only 1024. It's 64 times faster. If you've got 1024, and it's about 1 million multiplication, it's about 205 times faster. So people do not use DFT as a straightforward algorithm of calculating that summation. They use the FFT algorithm, which is a lot faster. How FFT algorithm works, you should learn that in the next course, which is in the 4th year course. So if you go back again to your program, all it says is that if you keep your data as power of 2, then you will be able to use the FFT, and which will be more efficient. And this is I don't need to go too detailed. This is the FFT of a speech signal, and if you take the Fourier transform of it, it just shows you, if you follow the envelope, these are the resonance frequency of your speech as an example. So just taking the fast Fourier transform of a speech signal at one particular frame, 256 sample, you can actually find the resonance frequency of the vocal tract. Summary. What's the summary of this chapter? What you should know. At the end of the chapter, you should know what is the definition of discrete time Fourier transform. DTFT. You know, given a filter magnitude response, how do you find the impulse response? I've done 2 examples. Then the properties of the discrete time Fourier transform. When to use discrete time Fourier transform, and when to use discrete Fourier transform. What's the difference? Where you use the discrete time Fourier transform is continuous. Discrete Fourier transform is just sample version of the continuum. Then when and how to use window for discrete Fourier transform. For speech signal you have to have window. You can't have small window. You can't have long window. Fast Fourier transform. The algorithm you haven't learned there, but the property. What is zero padding? And what's the relationship between the frequency resolution? What's the complexity between DFT and FFT? You don't need to derive the table, but you need to have some idea. Basically, that's the end of the chapter. That's part B, chapter 3. So far, part B we have completed. Chapter 1 is the transform. Chapter 2 is just basic Fourier analysis and Fourier transform. And then chapter 3 is discrete time Fourier transform and discrete Fourier transform and fast Fourier transform. So that's all on the transform method. So that's completed. So you should be able to go through this chapter, and if you get any problems, you can ask me in the discussion class or talk to the tutors. Okay, thank you.